Hey, in this video we're going to be talking about frame rate independence and Euler integration. So I left off where I said we need to fix this part of my code. I need frame rate independence and Euler integration. These are very specific requirements that I'm putting on my code here because there are a lot of games that mess this up, and I don't want to make one of those games. So what I mean is that there are games where the movement of the objects in the game depends on the frame rate, depends on how fast the game is running. And that can be a real playability problem if you get a new computer that's much better than your current computer, and your games start running faster. You can't control things because things are moving too fast. That's bad. You're playing with friends online, and your computers are running at different speeds, simulating the game differently. That's also a big problem. So I need to know something about how much actual time is passing, something related to real time. So I'm going to need what I'll call a delta time. So I'm going to scroll up, and outside of this main loop here, this while not done loop, I want to make a float. I'm going to call it dt. This is my delta time. I'll just start it off at 0 for now. And I also want to be able to measure how much time is passing. So I'm going to make a couple of integers that are going to be sort of like timestamps. They're going to say, this is the time that we started the frame, this is the time that we ended the frame, and then if you subtract those, you know how much time has passed. So I'm actually going to declare them using one of SDL's special types. That's a capital U int 32. It's a 32-bit unsigned integer, which just means it's the size of a normal integer and it's only positive. But I'm using this special type just because SDL does. So let me call this frame start, and I'll make another one frame end. And so when my frame starts, I'm going to get that time. There's an SDL function, SDL get ticks, that'll tell you the amount of milliseconds since your program started. So I have to remember that this is going to be a value in milliseconds, and if I want that in seconds, I have to divide by 1,000. So there's my start of the frame, and then when I'm all done, all the way at the bottom here, frame end is SDL get ticks. Alright, so call that function again to get a different time after we've all done our drawing and everything. Now I can take the difference. I can say dt is equal to the difference between these. Frame end will be greater, so I'll subtract frame start, end up with a positive value, and divide by 1,000 to get seconds. So now I have this delta time variable, dt, that tells me how many seconds have passed in one frame. It's going to be a small fraction of a second. And how I'm going to use that is here in my movement code, smile.y, instead of minus minus, I'll set up a variable. I'll just set it here. I'm going to just throw down some arbitrary number, and here I want to go minus equals speed times dt plus equals speed times dt, and so on. There. So now it's not just incrementing or decrementing every frame. It is changing according to this speed value that I've chosen. And so you may have seen this if you're taking GAM 230. You would see this in Unity as like transform.position plus equals something like this, velocity times time dot delta time. And this is the exact same thing. I have a position value, I'm increasing it according to this scaled velocity. And so this is a form of Euler integration. It's forward Euler integration. And if you've taken calculus, this is the same thing that they're talking about in calculus. You're taking small slices of one variable and adding them all together as another variable changes. So in this case, we have time that's changing. Time is moving on in small steps. So time.delta time or dt. And we are taking small slices of our speed and adding them in to our position so that our position changes over time. It's pretty cool. So in math class, integration is usually smooth and continuous. In computers, though, we need to take small steps, small chunky steps, in order to change these variables to kind of simulate that sort of smoothness. The smaller the time step, the better. We're going to get better results, more accurate, but it becomes more computationally expensive. So this is forward Euler integration, where you just have your velocity times the time step. But there are lots of other numerical integration methods, from like the midpoint method all the way to Runge-Kutta 4, RK4 if you're going to look it up. And they trade off this computational cost to achieve stability and accuracy, which Euler integration really has neither. It's kind of stinks at both of those, but it is really fast. For most games, if you're not like simulating planets moving around the sun or something, it's good enough. So we go with it. It's pretty common to find this code. Okay, so what we've done here is we have established a link between our actual time passing and the game time that's passing. So things are moving in our game according to the real time. And so we have achieved frame rate independence. So if I play this on a faster computer, it's going to run at the same speed. It's going to look like it runs the same speed. I might get more rapid refreshes from my screen, but it's still going to move my character the same way on every computer that I play. So there's some fun examples of games that have done this wrong. You can look them up. One of them that I had a lot of experience with was Lords of the Realm 2. And in that game, it wasn't that they didn't use frame rate independent code, it's that they partially used it, and that made it even worse. So some parts of the game stayed the same when I played it on a newer computer. But one part that did not stay the same was the rate of fire for archers. And my archers became like machine guns, mowing down enemy armies, and it was crazy. A lot of fun, but not exactly the way that the game was meant to be played. All right. So this is the steps that you have to go through to measure some time and establish frame rate independence in your game. There's some further techniques to take this and make it work even better. But this is pretty good for now, using a simple forward Euler integration scheme. I will see you later.